Generative machine learning for tabular data focuses on a single objective, transforming static CSV files into dynamic arrays of newly synthesized rows. This repository contains two distinct architectural models designed to solve that problem, existing side by side but utilizing very different mechanical logic. The first is DiffuTron, which represents a traditional approach built on flat vector diffusion. The second is DSFlow, a more recent alternative utilizing continuous time flow matching. While both models ingest the same training data and constraints, their internal processing pipelines follow completely different paths. These architectural choices determine how efficiently the models run and how precisely they can follow specific data requirements during generation. We can map these differences through the variant summary table to see exactly how these two stacks compare. For engineers, understanding this bifurcation is the first step toward building more reliable synthetic data pipelines. DiffuTron's architecture is built on a linear foundation, processing tabular data as a flat, sequential stream. This is a standard transformer setup. It uses a token per feature configuration with 6 layers, 8 heads, and a D model of 256 to process the flattened vector. DSFlow takes a different view, acknowledging that tabular data has specific row-to-column geometries that a simple flat sequence might overlook. To capture those relationships, DSFlow uses a dual-stream transformer. This architecture maintains a global row token while simultaneously processing individual local column features. This allows information to exchange between the row-level context and the specific column values, without collapsing the data's inherent structure. This interaction is optimized using flash attention to and one-dimensional rotary position embeddings, or ROPE. By utilizing this dual-stream topology, the model can preserve complex dimensional relationships that are often lost in flat sequences. Beyond the physical structure, the mathematical engines that actually generate the data are built on two very different objectives. DiffuTron uses a standard Gaussian DDPM. It relies on an epsilon prediction objective to denoise the data. This is computationally intensive. It follows a linear noise schedule that requires 1,000 denoising steps to reach a final result. DSFlow uses a hybrid approach, splitting its workload to better suit mixed tabular data types. It applies optimal transport conditional flow matching to numerical continuous data, treating generation as a smooth trajectory through a vector field. At the same time, it uses discrete reverse DDPM to handle categorical types, resolving both in a single pass. To keep these two objectives stable, the model uses an anti-collapse auxiliary loss on the token decoders, set to the lambda of 0.1. This hybridized math accelerates the generation process by significantly reducing the number of required iterations. While DiffuTron needs 1,000 steps, DSFlow produces samples in 20 steps, or just 10 steps using DPM++. By combining flow matching with discrete solvers, DSFlow reduces the generation bottleneck by a factor of 100 while maintaining data integrity. A major challenge in tabular synthesis is generation under constraints, forcing specific columns to stay fixed while the rest generate. DiffuTron handles this challenge through repaint masking. Repaint works by re-injecting the noisy target data at every single step of the denoising cycle. This brute force method is computationally heavy and can sometimes lead to coherence issues between the constrained and free columns. DSFlow uses a native mathematical alternative called constraint pinning. Because it uses OTCFM, the model allows the trajectory to naturally land exactly on the constraint value without needing to re-inject data at every step. We can also see a contrast in how these models manage classifier-free guidance alongside their constraints. DiffuTron uses an explicit null token at the num classes index to handle its guidance. DSFlow currently uses a more flexible but less rigid method of bypassing conditioning by passing y equals none. While DiffuTron has a more structured guidance pattern, DSFlow's native ODE pinning provides the mathematical guarantees for constraints that masking techniques struggle to match. Looking at the repository's backlog, it's clear that these two models offer techniques that can be cross-pollinated to improve performance. One priority is bringing DSFlow in line with DiffuTron's explicit classifier-free guidance pattern. By teaching DSFlow to learn a specific null embedding instead of just skipping cross-attention, the guidance becomes more principled and potentially more accurate. Another shared goal is expanding how both models handle numerical constraints. Instead of pinning to a single value, Engineers can clip the trajectory to stay within a high-low interval, allowing for range-based constraints. There are also specific upgrades that could make DiffuTron much more efficient, replacing repaint masking, improving information flow. Combining these strengths, like DiffuTron's guidance structure and DSFlow's native pinning, provides a clear path for refining the next generation of tabular models. Beyond shared ideas, each model has its own specialized frontier for optimization. For DiffuTron, swapping the standard scalar for a quantile transformer can reduce its sensitivity to the outliers often found in raw tabular data. For multi-column constraints, a jump-back repaint method can be used to improve joint coherence, even if it requires more compute. DSFlow's next step is fully enabling its temporal capabilities. While the training logic already supports temporal data shapes, the sampler needs to be extended to handle those same dimensions during generation. The most advanced mathematical upgrade would be retraining DSFlow for rectified flow. By using straight-line optimal transport paths, the model moves closer to the theoretical limit of single-step sampling. The transition from flat diffusion to temporal, rectified flow matching outlines the technical progression toward real-time, highly constrained synthetic data generation.